David Smith here with one more Flip Classroom math video. 3 tips before we start. First, you can increase or decrease the playback speed if that helps you get through the video. Second, you can pause the video at any time to catch up with your notes. Third, you can turn on the captions to watch my words go by on the bottom of your screen. All right, today's lesson is going to introduce you to the process of differentiation or taking the derivative. And we're going to get all over what that actually means first, and then I'm going to show you some rules for taking the derivatives. Okay, so check this out. My situation here is a falling body, okay? And what we're doing is we're tracking time on the x-axis, and we're tracking height on the y-axis. So we could be standing on top of a cliff or a building, and we're going to drop a ball off there. And that ball is going to drop down. Now we know its speed is increasing the whole time. So the height is dropping, here's time, and the height is dropping more and more quickly per unit time. And that shows up in the slope of the curve. So as you would expect, as it falls faster and faster, it's going to drop more height for the same amount of time. Now, there are some interesting questions we can ask about this situation, one of which is the speed of the object. Notice how this is not a speed versus time graph, it's a distance versus time graph. So the speed is not here, but we can calculate that, and that's what leads us to taking the derivative. All right, so we're going to approach this in a gradual way. So what if I'm wanting to know the speed here? How fast is it falling? So one approach would be, let's find the average speed between this time of x and then this time of x plus some h. We don't know what that is, but some value that we're going to add to x. So that's going to get us from time x to time x plus h. So that could be a second or 2 seconds or whatever it is that we're adding to our first time to get our second time. And then we can use our function here to find out what the height is at f of x. Notice how I didn't put any y's there. This is just f of x. We have a function underneath this that's governing the curve. And then the second height is going to be f of x plus h. So after a certain amount of time, h time, now our height is f of x plus h, whatever height that is. And that would be read on the vertical axis. So what we'd be doing is we're thinking about what is this straight line here. That's a secant line, and a secant line is a line that connects 2 points on a curve. And that's an important vocab for this unit. So I put a definition for a secant line right up there for you. Get that in your notes. Okay, so back to this. If I calculate the average speed between this time and that time, then I can figure I'm getting closer to finding out what the exact speed is at that point. So what would that be? Speed is distance divided by time. So what we would do to find the average speed between A and B is we do the change in height over the change in time. That's the definition of speed, change in distance over change in time. Our change in height is going to be f of x minus f of x plus h. Okay, so that is our height. We're dropping, so this would be a negative quantity. And then our time difference is going to be x plus h minus x. Because we end at this time, we start at that time, so the difference is going to be x plus h minus x. And then this ends up being f of x minus f of x plus h over h. Okay? So what we have here, h is our change in time, and this top bit, f of x minus f of x plus h, is our change in distance. Now what we're going to do to find the instantaneous speed is we're going to make h get smaller and smaller so that we get closer and closer to the speed, the instantaneous speed at the point, okay? And that would allow us to figure out what that speed would be. So right now, our speed is going to be the slope of this tangent line. But as we shrink h down, now I noticed that before I talked about finding the speed at b, actually what we're going to do is we're going to find the speed at a, because what we're doing is we're making h smaller and smaller. This tangent line, our b, is moving up this way. So you can imagine that if we made it really tiny, here's our b, let's call that a b prime, then our slope of our tangent line is just going to be really close to the slope at a. So what we're going to do is we're just going to make h smaller and smaller and smaller until it gets very close. Now here's the idea of a limit. We can't make h 0 because we'd be dividing by 0, but we can make h very, very close to 0. So, and here's what we're trying to find, is we're trying to find the slope of a tangent line at a. So that tangent line slope, that is our instantaneous rate at a. So notice how that the secant lines are going to get a little bit less steep as we get closer and closer to a, until when we take the limit of this function as h goes to 0, we're going to get the slope of the tangent line, which is the instantaneous speed. Okay, just a little bit of language here, and then we're going to jump into the derivative rules, which are actually pretty straightforward to use. So, if we want the derivative of f of x, this would be a derivative function that we could then use to figure out the instantaneous speed at any point on that curve. Here's the notation we use. F prime of x is the derivative of f of x. We can also use dy dx to express the derivative of f of x. So let's take a look at some differentiation rules, how they're used to find the derivative function for a given function. All right, our first rule is called the power rule. And basically this helps you find the derivative of a function with a single term that's raised to a power. So if f of x is x to the n, we're going to use n as our power in these rules. Then f prime of x, in other words, the derivative of x to the n, is just going to be take the n, put it in front of the x, subtract 1 from that power, and that's what's remaining. So pause the video, see if you can use that rule to find the derivative function of this function. Actually, what I did is I put it in notation so that I can prompt you with f prime of x equals. So now pause the video and use this rule on this function and come back. Okay, let's see how you did. All I did is I just took the n and put it in front of the x. So the n is 2, so now that's 2x. And then I took the n and subtracted 1 from it and put that there. So check it out now. X to the 1 is just x. So the derivative function for 2x squared, or for x squared, is just 2x. Let me give you another one. Okay, let's do these one at a time. Here's your first one, very similar to the last one. F of x equals x to the 6. Pause the video and find your f prime of x, your derivative function. So all we did is we just took the 6, put it in front of the x, reduced the 6 by 1. So our derivative function for x to the 6th is 6x to the 5th power. Okay, now we're going to get a little more tricky. You're going to need to remember your rules of exponents. So if f of x is root x, what is f prime of x going to make? Now pause the video, see if you can do that. Okay, so if you're back and you haven't done that, you have to realize how to write square root of x as a power. And the way to do that is the root is the 1/2 power. So this is x to the 1/2. So go ahead, pause the video, and convert that using our power rule to the derivative function. Okay, so here's what I did. This is x to the 1/2 power. So I took that 1/2, put it in front of my x, then I reduced the 1/2 power by 1, which gave me x to the negative 1/2. Now this could be fully simplified, get rid of some of these fractions. Okay, so notice how I've got a negative power. We tend to get the cut action. Okay, so let's see how that simplifies out. We don't like negative powers. Okay, we don't like fractional powers either if we can deal with those. So everything is going to go underneath. We have a 2 that's underneath on the fraction. We have x to the 1/2 to the negative 1/2. So this becomes 1 over 2x to the 1/2. So we got that power expressed positively. Now we need to get rid of the fraction. So remember, x to the 1/2 is the same as root x. So this becomes 1 over 2 root x. Okay, let's do this last one. Now I changed it from how I had it written on the board, so go back to your notes. We're going to do 1 over x to the 4th, not x to the 1/4 power. So see if you can figure out how that one goes. All right, I want to show you a step that you might have done that's not correct. It makes sense, but it's not correct. Notice how we can apply the derivative rule, the power rule, to this term here and get 1 over 4x to the 3rd. I'm just following our rule here with my x to the 4th power. But notice how our rule is not for 1 over x to the n. It's not. It's just for x to the n. So we can't apply that rule directly here. We have to do one step first. So go ahead and pause the video and see if you can figure out what that step might be. So that step is to bring this power up. We just take it from being positive to negative. So 1 over x to the 4 is the same as x to the minus 4. Now, pause the video, use your power rule, and find the derivative function of this one. All right, using the power rule means I take my minus 4, put it in front, minus 4x, and I subtract 1 from my negative 4. That leaves me with negative 5. Now, this is a good answer. If I'm wanting to have positive exponents, then I can bring this back down to the bottom and do negative 4 over x to the 5th. And notice how that is definitely not the same as that one answer I showed you a minute ago. Okay, so the next two rules, all we're going to do is we're just going to add on to the power rule. So these rules allow us to analyze more complex functions, but essentially what we're doing is we are incorporating the power rule in a couple other situations. So here's the new situation, the constant multiple rule. Now we have an a in front of our x to whatever power. So we just have a coefficient of our term, of our exponential term. So the rule for that is we just take the n, bring it down, and then multiply it by that a. And then as before, we just subtract the power by 1. So now pause the video and find this for me. F of x is 3x to the 3rd. Go ahead and find the derivative function of that one. So I just took my n and multiplied it by my a, so I have my 3 times 3 there, and then I'm reducing this by 1, so that's 3 minus 1. I'm just breaking it out into very obvious steps. So then I just combine my numbers, do my multiplication, and I have 9x squared. So the derivative function of 3x to the 3rd is 9x squared. All right, 2 more for you to try. Go ahead and pause the video and find the derivative function for that one and for that one. When you got those done, come back. Okay, let's take a look at this first one. Again, I can't take a derivative with the power rule when it's in the bottom of a fraction. So I just brought that up, made it minus 12. So this becomes 3x to the minus 12. Now the derivative function, I'm just going to take my minus 12, multiply it by my 3, get minus 36, decrease my power by 1, which gives me x, the negative 13th power. And then I like to have no negative powers, so I brought it down here. Either of these answers are good. So there you have the first one. Now the second one is a little bit more straightforward. I can just do the derivative rule on the top of my fraction. So I get minus 12x to the minus 3. Now I have minus 12 over 12. That's going to cancel down to be a minus 1 or just a negative. And then here's my negative 3. Now again, I like to have positive powers, so I brought it down. I have minus 1 over x to the 3rd. So that's those two problems. All right, so the last one is the sum or difference rule. And what this rule allows us to do is differentiate a function with multiple terms. So let's take a look at the rule in a general form, and then we'll pull it together with some examples. So check this out. So if f of x has two little functions in it, like u of x and v of x, now I'll make this clear in a minute exactly what this all means, because I think this is a little bit of a confusing kind of a notation. However, let's keep going. So if f of x is this function u of x plus or minus v of x, then f prime of x is just going to be u prime of x plus or minus v prime of x. Okay, so let's see how that works. Here we are, f of x, here's our u of x and our v of x. So all we do to find the derivative function for f of x, f prime of x, we just take the derivative of this term, and since it's plus, we're going to do the plus part there, and add it to the derivative of that term. Now those two things you can do using the power rule. So watch that. This becomes 6x squared plus 6x. Okay? So pretty simple. I just did the power rule to that one and the power rule to that one. So my derivative function for for f of x is 6x squared plus 6x. All right, let me give you a more complex one, and it's going to tease out a couple applications of the power rule that we have not done yet. So check this out. Here's our function, 4 terms. So when we take the derivative, we're going to take the derivative of each of these 4 terms. So check it out. We got 7x to the third minus 4x squared plus 2x minus 7. Now the new terms in this one are your 2x and your 7. Now we can use the power rule on those terms, but you just have to think a little bit, especially for taking the derivative of the constant 7. All right, so I did the first 2 terms. Those are straightforward applications. This becomes 21x squared, and then this one becomes minus 8x because that's x to the 1. But how about 2x? The trick here is to realize that this is 2x to the first power. So pause the video, create that derivative. So the derivative of 2x to the first is just 2, because I take my 1, I bring it down and multiply it by the 2, so that gives me a 2. Now, x to the 1 minus 1 is x to the 0, which is just 1. So that goes away. So this one just becomes 2. Now, think about what this is with an exponent on x. Here's the trick. The constant can be seen as itself, minus 7, times x to the 0. Remember, x to the 0 is just 1. So that's what this is. 7 minus 7 is really minus 7 times x to the 0. Now when I use my derivative rule when I use my power rule on this term, something interesting happens. Think about that for a minute and then come back and write your answer. So when I bring my power down and multiply it by my coefficient, I'm going to have 0 times negative 7. So no matter what I would do with x, maybe make it negative 1, the whole thing is going to be multiplied by 0. So this goes to 0. So the answer is, whenever you take the derivative of a constant, it just goes away. So notice how I erased my minus. Here is my derivative function for that function. All right? Try this one. I'm not going to prompt you. There's a step you need to do first, and then you can take your derivative. All right, so to do this, I don't have any powers. This is a factored expression. This is a quadratic in factored form. So what I did is I FOILed that. I end up with my function as being x squared minus x minus 2, and now I can use my sum or difference rule and my power rule and all my other rules to figure out what the derivative of that function is, which is 2x minus 1. This one's a little tricky, because I have a nice big polynomial over an x squared term, and there's no obvious way to apply all of our rules to that. So there's a trick we can do that will help us do that. So go ahead, pause the video, see if you can figure out how to change this expression around so that we could do that. All right, so my first trick is to take this function and make it into 3 terms, because my rules really only let me apply my power rule and my power rule to individual terms, and this is all kind of moshed together. So normally we do this, we simplify by getting common denominators. Now we're going to break it out. So basically this is just this term over x squared, this one over x squared, and that one over x squared. So that's what I wrote there. Now, we're not quite yet ready. There's one more step we need to do to this function to be able to apply some derivative rules. Now we can take the derivative. So check this out. I just reduced my fractions, and then I made this one go up on the positive side. So I have an 2x to the fourth over x squared. That just becomes 2x squared. The same with the second term, reduces down to minus 3x, and then 1 over x squared is x to the minus 2. Now, what I want you to do is pause the video and use your sum or difference rule with your power rule and find me the derivative function of that function. All right, let's see how you did. Here is my derivative function. I just took my derivative of my 3 terms. Notice how this one I didn't bother to change the exponent to a positive because it's in a multi-term expression. So that makes the most sense for this one. So right now, you've just received a whole bunch of mechanical rules, algebraic rules, for converting functions into their derivative functions. Now, as we move on through this unit, you will find out, we'll get a better picture of the context. What are we doing when we take the derivative? And that goes back to that graph in the beginning where we found the instantaneous rate of change. Now that you've watched the video, take a moment to jot down any remaining questions so you can bring them to our next class. Remember, you can also come back to this video again and watch it for deeper understanding. If you liked or enjoyed the video, please click like or subscribe down below.